Hi everybody, in this video we are going to learn how to design a microservice using AWS Lambda. This can be thought of as my extended version of my AWS re:Invent dev chat I did at re:Invent. In fact, the majority of the content in these slides are from that chat, and the sample code that I show is also from the chat. I just added some materials that I had to cut out when I was limited to a 30-minute time frame, which with my fast talking from my nerves got somehow down to 22 minutes. So let's get started. So let's first break down what this video is going to contain. We're first going to learn about the problem that we're trying to solve, which is why we are designing this microservice. And then we're going to do a quick review of event-based architecture and AWS Lambda. It's a very fast review, but this video is broken up into sections. So if you don't want to watch this part, you can just skip right ahead to designing the microservice. In this part, we are going to review the high-level architectural design for the microservice that we are building. And then we are going to look at the code and how we would deploy the solution. After that, we are going to go through the pros and cons of that design that we just talked about. And finally, I'm going to leave you with a few takeaways so that you can decide whether or not this design is actually appropriate for you. Because, spoilers, it's not appropriate for everything that you design. So first, the problem. Let's imagine in this scenario, you work at a startup company, and this startup company is in the world of health tech. And this is a startup, it's starting from ground one, and you've been tasked with building a microservice to handle all the patient information. And for a little more background, your company's cloud provider is AWS, and you've been told to just get this work done as quickly and as cheaply as possible. Well, you think, hey, I know enough about AWS to be dangerous. Why even build a traditional microservice that's within a container? Technically, everything can be translated down to event-based actions. Why not use AWS Lambda instead? So I just said technically everything can be translated down to event-based actions. This means we are going to use an event-based architecture. So event-based architecture uses events to trigger and communicate between decoupled services. This is very common in modern applications built with microservices. In event-based architecture, an event is a change in state, or it can be an update. So it could be like when you're on Amazon and you place an item in your shopping cart. Events can even carry a state, like the item that's being purchased or the price. And events can also be identifiers, like a notification that an order was shipped. So event-driven architectures have three key components. Event producers, which publish an event to the router. The event router, which filters and pushes the event to the event consumers. Producer services and consumer services are then decoupled, which allows them to be scaled and updated and deployed independently. And this is all important to know because AWS Lambda integrates with other AWS services to invoke functions based on the events that you specify. Lambda is a compute service that lets you run your code, the function, only when needed, and it scales automatically. Lambda runs your code in high availability compute infrastructure, and it performs all of the administration of the compute resources, including the server and operating system maintenance, the capacity provisioning, and the automatic scaling and logging. It just makes your life really simple. So we just did a quick review of event-based architecture and AWS Lambda. So let's understand now the Lambda lifecycle. So the AWS Lambda lifecycle consists of three phases: the init phase, the invoke phase, and the shutdown phase. Our init phase is where we initialize our extension, then we initialize our runtime environment, and we also initialize our function. Invoke then is called after, and within the invoke phase, the function code is invoked. When invoke finishes, there is an idle period. If a Lambda event gets called again, it will actually use the same runtime environment, so it doesn't need to go through this init phase, and it will invoke again. But this idle time is short, and after the functions are completed, after that idle time expires, it goes through a runtime shutdown, and the extensions that may have been also initialized will be shut down as well. Your shutdown phase is limited to about 2 seconds. If it doesn't shut down within that time, Lambda will just automatically kill it with a sig kill call. This is the Lambda lifecycle, and it's important to understand how Lambdas live. So if your Lambda function isn't called frequently, it's just called once in a while, that idle period is going to happen. So every time the Lambda function is invoked, you're just going to always have to reinitialize and then invoke, and then you have your shutdown. If it's has more heavy traffic, then you might have Lambda functions that are running in the same runtime environment. But make sure that you understand you should never assume that a Lambda function is going to be running in the same Lambda environment. You should treat your Lambda functions as stateless. So you're caught up. We're writing a microservice using AWS Lambda. Now, every good developer knows to design before you just jump in and start coding. So that's what we are going to do. We're going to design the microservice. And at this point, we're going to review a high-level architectural design for this solution. We're designing our microservice to use AWS Lambda, and we're essentially making our microservice without servers, right? It's just not my EC2 instance. So overall, the high-level design is relatively simple. We here have the client, and the client goes through the API gateway, which then our endpoints for our microservice will be defined as functions. That then write to a data source of our choice. In this case, it is writing to an RDS cluster. Patients tend to be relational, and on a first glance, this seems like a pretty good idea. So this really does seem pretty simple. But if we think about the fact that each Lambda is a separate function, well, things can get a little messy. And if we want to use things like multi-tenant, well, it's getting even messier. What I'm getting at is that these functions are separate, but they share common code. And our goal should be to keep the footprint of our Lambda function relatively small. And we also want to keep it efficient. So we have to ask a question. How can we share common code across our AWS Lambda functions? So first, let's identify our common components. So you notice at the center of this diagram, we have a microservice. And within the microservice, we have all the fun business logic, getting patient data, obfuscating PHI, all the works that come along with building a patient API for a health tech company that needs to be compliant with HIPAA and other security measures. But surrounding this, we have common components that would need to be shared by any microservice that would be part of our system. An obvious shared component would be the authorization. We don't want anybody just coming in and accessing our microservice, so we should have an authorization layer. And with this authorization layer, we can even grab information from a JOT to determine a user ID or a tenant ID. Then another obvious shared component we have is accessing the data. In the case of our example earlier, all the functions were accessing a RDS cluster. But this could be anything. It could be accessing an S3 bucket. It could be accessing a DynamoDB, whatever you can think of. This is that data access layer that we have. Now, there are some less obvious components. We want to capture and log our messages. So a logging component would need to exist as well. And then finally, we want to record any metric data, and that's associated with this service. So we need a metrics component. All this isn't really unique. Most microservices should have similar shared components, but this is another complexity that would need to be added when we need to implement our microservice. And also, if we take these services and place them in a multi-tenant environment, we find that there's even a bigger range of additional considerations that will impact the scope and the implementation of our functions. So removing that complexity from our base microservice is actually better. So what you can see here is we need to have shared libraries. So how do we realize this in a serverless model? Well, let's look at our Lambda functions in a different way. So here, every function is required to keep track of the authorization, the logging, the metrics, and the data. And when the function is deployed, it will have to deploy to all of those models. But if we use Lambda Layers, then the function instead references the auth layer, the logging layer, and the metrics and data layer outside of the function. By using Lambda Layers, we not only get a convenient way to package our libraries and other dependencies, but we also reduce the size of the uploaded deployment archives. And this makes it faster to deploy the code. So Lambda Layers, we get a smaller deployment package, and we also get easier maintenance. Also, with Lambda Layers, you can push a lot of the multi-tenant awareness out of your Lambda functions and into a layer that supports tenant abstraction. Lambda Layers also add more agility to a project because each layer we introduce can be versioned and deployed independently. So we make updates to these shared libraries, and then we have individual functions that opt into the newer version of that layer. So let's discuss the code. So here I have the example code that I showed at AWS Re event. And we're going to walk through the get patient function. So this is the patient service. This will get a specific patient by their patient ID. So it receives an event, and when it receives the event, it logs that message to a logging layer. And then it calls the data access layer for the patient database. So in this case, it calls our data layer for get patient, passes in the event, and when we receive back our result, we log the metric. In this case, it's a very simple metric. We're just recording how long the get patient call took before it responds back. And this is just so we can keep track of how long querying our database takes. First, let's look into our DAL for our get patient. Our get patient call, in this case, we were saying we're doing RDS cluster. This is a Postgres database, and it's going to connect to our Postgres database based off the credentials that are passed in, and then it will connect. If it errors on connecting, it's going to log that information, and if it successfully connects, it will also log the information. Then it calls a simple select, and then processes that information and return the results, whether it be an error because the query failed, or it will return back a success with the results that are given. In this case, it's actually even creating a response with a 500 or a 200, whatever you want to do. So you handle those different errors based on you want. And actually, you could even get a little crazy here and make a layer that actually creates responses based off of error messages. But we're making a simple service, so thinking simple right now. This is a simple call into retrieving a patient. We've also have the log manager. We've been calling this a few times to log specific events. So let's look into that. The log manager, like I said before, logs a message or an event. And within the log manager, it uses the token manager to retrieve the user ID. In this case, for the token manager, it takes in the JOT token that is part of the call. This is part of that authorization layer that we have to have. It retrieves that JOT. It will then read the JOT and find the user ID. And if there's a problem verifying a token, it's going to log the error. You can even do this to find other parts of the JOT's body. For example, the tenant ID, if you wanted to find the tenant. So going back to the log manager, we get our user ID, we log then our source by calling the logs data access layer. If we look at the logs data access layer, this logs an event to a DynamoDB. You could also log to an S3 bucket or anything that you want to do. In this case, the example was a DynamoDB that just holds in a random UUID that has been generated and the message that we are passing in. And in that message is the user ID of who invoked that call. Now, going back to our patient service, we have then the metric manager. The metric manager is very similar to our log manager. It extracts the user ID from the JOT that has been passed in, and then it logs the metric event. Takes in that event source that's being passed in, it takes in all the duration and the time, then it calls the metrics data access layer, which again is another DynamoDB that logs our metrics. Again, this can be done in something other than DynamoDB. It can be an S3 bucket, like I've mentioned before, or anything else that makes sense to you. You can think about this and call something like segment if you wanted to, and do all your metrics being done in a tool like that. This is just a very simple example. So think about it in a way to integrate those other tools that you might use. Thinking about with logging messages or events, in that case, you might want to call Google Analytics. Or, like I mentioned before, you're doing a call that instead of directly calling Google Analytics, doing segment, and segment handles that. These are all options that you can do. This is just the simple example. So this is the high-level architecture that we've done with Lambda layers broken down into code. And then in order to deploy this code, you can use Terraform, or in my case, I'm using serverless framework. So serverless framework, here we set up our parameters for prod or dev based on how we're deploying it. And then we define our layers with where the path is for our layer. And then our function are defined as well. In this case, it's get patient, create patient, etc. with the HTTP's API with the path that it's at, what the method is, and the layers that are being referenced. In this case, the layer exists in this code. So when we're deploying it, I'm talking about the reference is going to be specifically be these layers, and the layer's name, and when it's in the code, is the name of this. So in this case, it's dependencies, Lambda layer. If you wanted to use a Lambda layer that's already deployed somewhere else, then you would just use the cloud formations reference here. Then you follow this normal serverless standards where you can deploy a specific function or you deploy the overall code. So serverless deploy. Now again, this is a high-level overview, and you may have to play around with it a little bit to make it work for your environment or the way that you like it. If you want to do Terraform versus serverless framework, that's right up your alley. You go ahead and do that. Now, I've shown you the code, giving you a rough idea on how to deploy the code. So here comes the fun part. We are going to talk about the pros and the cons of this design. So first, let's discuss the pros. The pros are very similar to working with AWS Lambda functions. It saves time and effort. You could probably imagine spinning up this microservice doesn't take much time. And this is one of the major benefits of going serverless using AWS Lambda functions in general. You save the time and effort for creating and maintaining infrastructure for your application. The next pro is that it's low cost. You pay only for what compute time you consume. No more idle servers, wasting money, and waiting for requests. So you're just spending it on the time that it is being used. Also, AWS Lambda improves scalability. Functions run in response to events, and the more events that are triggered, the more instances of the function will exist. And finally, it's highly available. This solution will not be locked into a single data center or availability zone. But this talk wasn't just about designing a microservice using AWS Lambda and how great it is. This talk is also to discuss the cons of doing this type of implementation. So, a very big con. There is no local dev. And okay, this isn't a big problem for the CEO of GitHub who thinks that in a few years there will be no more code on your local computer. But for all of us living in the present and actually coding still, with AWS Lambda, local development isn't a first-class option. You are able to manually invoke a specific function on demand, but you can't call an app like you would with a traditional REST API on localhost. And that means that you can't use proper tools like curl or Postman or Swagger without code changes. Now, there is other tooling available for example, Amazon provides AWS serverless application model, or SAM, which allows you to run code one function at a time. Serverless framework allows you to invoke a function as well locally. You still have to set up an account to hit certain things like your DynamoDB in order to write to it. And then you can use things like LocalStack, which is an emulator. But that's not really ideal because it's not exactly like the real AWS and it's expensive. You could also use AVM, AWS Vending Machine, but again, this option means more money and sometimes more problems. Now, the absence of local dev could be offset by adding more debugging tools, but right now, with the Lambda execution on AWS, there's no way to run a traditional debugger. So you can't really step through your code and set breakpoints and figure out your issues. So you gotta rely on cloud logs. And this is a contrast to that traditional local dev where you can simply kind of look at your terminal or your log file and see what's happening. So this is a mindset change. It might not be a deal breaker for you. For some, it is. But if you want to go forward and do a design like this, you have to be ready for the time that it's going to be challenging to test your code and also diagnose a production issue. The next con is that your framework and your code may need to change. An engineering team might find the perfect solution for a problem at hand in a more reusable framework or library, but they could struggle to get it to run on Lambda. Another thing is, if you want to go to AWS Lambda and you're a bunch of C++ devs, well, you're going to have to learn a new language because C++ isn't in Lambda. Another thing, especially with this design, is automatic scaling can lead to a denial of service attack against yourself. It's really easy to shoot yourself in the foot with automatic scaling if your downstream tools are not ready for it yet, right? Lambda scales up, and if your downstream services, like a database connection pool, are not ready, so you have to be prepared. For example, in the design that we did right now, if we just had one Postgres instance and it was really tiny and small and it just wasn't ready, we could actually just crash our server. So we don't want to do that. So maybe we would want to instead design our patient database using DynamoDB so it could scale as well. So you need to be aware of your downstream services. This is an easy example to point at because we designed the whole thing from scratch. But if you're using older systems that aren't ready to be upgraded and are not ready to be expanded upon, then you might need to think about how you could throttle your Lambda so it doesn't scale automatically and crash those services. The major benefit of Lambda is that the operating system vulnerabilities and all those concerns that we have within our traditional web apps, they kind of go away. But programming languages are also mandated and enforced. So Lambdas need to be maintained and regularly upgraded. It's not really a big deal. You should, a project never truly dies until it's not running anymore. So you should be watching your code and making sure that you're upgrading it. But this can also be challenging and a pain point because when you try to be proactive, you will find that Lambda has a slow adoption of the latest programming releases. Until the middle of November, Node.js 18 was not available for AWS Lambda, even though it came out in April. For the latest stable version for Python is not available right now on AWS Lambda. Even if you want to get ahead of a deprecation policy and move to the latest LTS, Lambda may not be there yet. Yes, I was speaking at an AWS conference, but I needed to address the elephant in the room. That design that I gave could only work in an AWS environment. You have just locked yourself in to using AWS. This is in contrast to a container-based service, which would allow for migration if necessary. So if you cared about flexibility, well, you've kind of lost it by doing this type of design. The final con is that Lambdas have quotas, and these are limitations that developers have to take into account. And they must spend time tuning properly, or you can work with AWS to expand on them. But some quotas to address is that your Lambda, that if you have your Lambda handle an API call like we had before, it cannot exceed 6 megabytes for a request and response. Another quota is that a Lambda should not run longer than 15 minutes. This may not be a problem with an API call. You're not really going to have Lambdas that take 15 minutes, but it is something that you need to keep in mind. The memory by default is 128 megabytes. It can be manually configured up to 10 gigabytes, but you gotta be careful about that. The more you up the memory, the more expensive it gets. Finally, each AWS account only allows for a total of 75 gigabytes of Lambda storage in each region. And this means that make sure that when you deploy, you clean up your previous versions. You have to make sure that you do this, otherwise it'll grow out of control. This is best practices. But the reason I'm bringing this up is that I have worked at places where they did not clean up. And one day the team couldn't deploy to dev and they couldn't figure out why. Well, that was why. So this one's more of a housekeeping thing for you to know, because we shouldn't expect everything to be infinite. And it's kind of a waste of space anyways, so you should clean up, but I wanted to bring it up because it does occur. So what should you take away? Lambda isn't a general purpose solution. It's not appropriate for all use cases. For example, high availability services with low latency. This is because what I showed before with the Lambda lifecycle is that our cold start times can make it a bad fit for these type of services. These type of services can be like auth or financial processing. And you can configure it to be provision concurrency, but then it's no longer serverless, and that defeats the purpose of a serverless solution. Shouldn't use this for UI applications that are pure static content. This is far better to use a infrastructure like CloudFront or S3. It's not going to be a good fit for WebSocket apps. So if you're thinking of making your microservice serve a front-end application that needs a WebSocket, Well, most user sessions stay open for longer than 15 minutes. You've just reached that Lambda quota. It's not going to work, so don't do it. It's also not a good fit for big data apps where there's a lot of heavy processing jobs. And also with big data apps, it doesn't need to be in the now. So you should use something more like EMR or Glue. That is to another thing is that it's also not a good fit for heavy mathematical computations like number crunching. It's not a good idea because we're going to be maxing our CPU, we might be hitting our Lambda quotas on our memory, and we could also be hitting our time limits. Now, finally, you also should not use this solution for a stateful service. Lambdas, as we saw with the Lambda cycle, are stateless. So do not try to use this for a system that needs to always be on and stateful. So before you jump out and start solving your problem using AWS Lambda, before you start designing your microservice using AWS Lambda, make sure you truly understand the problem you're trying to solve. You also need to take into account what your team's knowledge is and the limitations that they may have. You don't want to force a bunch of C++ devs to use Lambda tomorrow. It's going to be messy. It's not going to start off quickly. And it's just going to lead to a lot of frustration. You need to level up your team first. And you also need to think about what you, the company, and yourself value. Maybe you value flexibility or the control or the options, or it's just low cost and getting it up as quickly as possible. And you guys all know nodes, so let's just do it. That is important to take into account. I'm not saying don't write a microservice using AWS Lambda. I'm actually saying write it. Go ahead. If you know that everything you're doing is fine, you will be great. But make sure you do truly know the problem you are solving. Because once you get to those points, because if you start falling into the trap and trying to design a big data application using AWS Lambda, you got a problem and you need to know to pivot to another solution. So I hope that you found this talk valuable and you have some things to take away and think about when you're moving forward with your AWS journey. And if you liked what you saw, please subscribe to my channel so that you can get notified of other AWS tutorials and other programming videos that I may upload. And until next time, happy learning.